Welcome back, students, to this module number 21, where we are going to learn about the very famous Gamow's theory of alpha decay. We are going to only look at it from the qualitative treatment point of view. We will not go into quantitative one. So we will only understand and get some explanation and what it means about or what Gamow tried to convince from his theory of alpha decay. That is what we are going to look at. Fine. Alright, and of course at the end of it you need to have a basic knowledge about the Gamow's theory of alpha decay. So to begin with, we need to understand why Gamow's theory is required to understand alpha decay, okay, to understand this entire process of alpha decay, because of the fact that the alpha particle emission presented a difficult theoretical problems, okay, which is brought out clearly when the spontaneous emission of alpha particle by nucleus is compared with the scattering of alpha particle by the same nucleus. Okay, so when there was a theoretical comparison between the energy of the particle that came out during the emission of the alpha particle, compared it to the energy of the alpha particle which was there, okay, during the scattering. Okay, so the two energies, when they were compared, there was kind of a contradiction, okay, called alpha decay paradox. Let's try to understand it. Okay, let's try to understand it. Let's take an example and understand it. So we have this example of uranium-238 getting decayed to thorium-234. Okay, giving out an alpha particle with some alpha disintegration energy QA. Okay, we have used E alpha in the previous module, so this is from the reference book that I'm using, QA. You can use E alpha also. Now, the kinetic energy of the alpha particle in this, okay, the alpha particle that came out during the decay of uranium-238 to thorium-234 was roughly or approximately 4.2 mega electron volts. Okay, 4.2 mega electron volts, the energy with which the alpha particle came out from the uranium-238 nucleus. All right, no problem here, no problem. But look at the next example that we have. Next example is of polonium-212, which gives out kinetic energy, which also undergoes decay and gives out kinetic energy of having energy of 9.9 mega electron volts. Okay, the uranium decay give you alpha particle having approximate energy of 4.2 mega electron volts. Here we have polonium, which gives out alpha particle of 9 mega electron volt. And when this was made to or was shined onto a uranium nuclei, it was found that they get scattered. They get scattered by uranium. Instead of getting absorbed by nuclei of the uranium, instead of getting absorbed by the nuclei of uranium, they are getting scattered by the same uranium nuclei. Okay, it was the same uranium nuclei which was giving out alpha particle at 4.2 mega electron volt energy, but is refusing or is not allowing an alpha particle of energy or almost a double of energy to enter into it. Okay, so this was a big paradox. Okay, so clearly, as you can see, that it's unable to cross this repulsive Coulomb potential barrier. We can clearly see that a higher energy is not able to clear the Coulomb's repulsive potential barrier, but a lower energy is very easily crossing its own potential barrier. Okay, it's very easily doing it. So that was a paradox. Just like if I give you a very vague example here, you can see this window here, and I'm saying that this block of same size is very easily crossing this window, very easily crossing, no problem. But then I'm saying that this block, which is 1/4 the size of that same block, is unable to cross this. I know it's a very bad example, but good enough to understand the paradox in what is happening in the alpha decay. Okay, so a big one is unable, in this case the big one is very easily crossing, whereas a small one is not crossing the same window. Okay, over there a particle with higher energy is not able to go into the nucleus, whereas the particle with almost half the energy is coming out of the nucleus, right? Okay, so that was the paradox that the Gamow tried to solve. Okay, let's get a little bit more technical by taking the potential energy diagram. Okay, so considering the nature of the force experienced by the incident alpha particle, a nucleus can be represented by a potential value. Okay, so let the height of the potential be Vp, and the range or the length will be Rn, okay, and then we have this particle coming from outside, okay, as you can see it's increasing, okay. So this particle which is coming from the right side, okay, it will be able to get into the potential, okay, only if the potential energy, or initially it is possessing a lot of kinetic energy which is getting converted to potential energy, and only if the potential energy is higher than the potential energy of the potential well, only then it will be able to cross this potential well and get into the potential well which is on this side, okay. Same is the situation for the particle which is there in the potential well. It will be able to come out of the potential well only if it possesses enough potential energy, or potential energy greater than the potential well to come out of it. Fine, all right. Of course it will have an energy of E alpha. Fine. Now the classical physics is unable to explain this phenomenon. According to classical physics, it is quite straightforward that if a particle possesses that much of potential energy, only then it will be able to get into the potential well or come out of the potential well. However, we have come across our topic of tunnel effect in quantum mechanics, right? In your previous semester in quantum mechanics, you might have definitely come across this topic of tunnel effect, where they have given some probability of the waves, the incident wave, to get transmitted, to get passed through a potential well having potential higher than its actual energy, okay. That was called tunnel effect, and the phenomena of this was explained by Gamow. This theory is named after the person whose name after this theory is named, and also independently by Condon and Gurney. All right. So to understand this tunnel effect, let's get little bit basics of what we understood in tunnel effect in quantum mechanics. Okay, in quantum mechanics, you were given a potential well with potential barrier of length L having potential V naught, and then there was an incident particle from left side coming into this, and there was some potential, some probability of passing out or transmitting through the potential, even though it didn't have that much of potential required to pass through the potential well. Fine. Now coming back to understand our nucleus, so we have on the right side the kinetic energy of the particle, and it getting converted to potential energy as it reaches very close to the nucleus, okay, and will be able to get into the potential well only if it gains enough potential to cross through the barrier. Fine, okay, and same would be the story for it to pass from the left to the right side, okay. So if it has energy of E alpha, and this would be the situation, right? These were the basics that we learned in tunnel effect. And you also came up to the expression of transmission probability T equal to e raised to minus 2 K2L, where K2 was equal to square root of 2m h cross V naught minus E. M is the mass of the particle, V naught is the potential, and E is the energy. Okay, of course, in this particular Gamow's theory, we replace V naught by V of R, and the transmission coefficient T gets equal to e raised to minus 2. Instead of simply K2, we have it integrated from 0 to L. Why? Because this area we are now trying to integrate. Okay, so if we can split this area, okay, if we can split this area into fine strips, okay, fine strip of width dx each, and then we can find the area of this by just integrating it from 0 to L, where L is the length of the potential barrier, okay, length of the potential barrier. So if you do that, we will get this expression for transmission coefficient T is equal to e raised to minus 2 integrated from 0 to L. L is the potential barrier, K2 dx, okay. And of course, doing some more mathematical steps through which we are not going to, you will get a final expression for this barrier penetration constant or transmission coefficient, okay. The probability for this tunnel effect to take place, that is T, will be equal to e raised to minus 2 square root of 2m h cross integrated from Rn to 1, okay, 0 to L in this case, okay. V of R minus E raised to half dr, okay, where V of R is equal to 2ze square upon 4 pi epsilon naught R, right? So the probability that the nucleus will emit an alpha particle in unit time is given by the product of the penetration probability T and the frequency V alpha by 2 Rn. Now to get a bit more or understand this bit more, let me just give you a small numbers here. If I give you an alpha particle whose mass will be 6.64 into 10 raised to negative 27 kilogram. In fact, two more digits are there, but let's constrain it to two decimals after two numbers after the decimal. So 6.64 into 10 raised to negative 27 kilograms. And having say kinetic energy 5 mega electron volt, height of the barrier be 20 mega electron volt, and the width barrier of 10 Fermi. Okay, some numbers which are actually existing for any nucleus. Okay, so if we use these numbers and calculate the transmission probability, you will find that it is approximately 5.9, that is 6. Okay, approximately 6 in every 10 raised to 15 collisions against the barrier. If you are listening to this lecture very carefully, this number should give you some kind of a feel when you are listening to it. Okay, a particle makes 10 raised to 15 attempts. Okay, a particle makes 10 raised to 15 attempts to trying to pass through the barrier, and the only chance that it gets to come out of the barrier is 5.9, that is 6. So it is successful only 6 times out of 10 raised to 15 attempts it does to cross that barrier. Amazing, right? Okay, so this tunneling effect that we talk about, the probability of tunnel effect to take place that we are talking about, is only 6 out of 10 raised to 15 total attempts that it would make in its lifetime, right? Okay, so moving on further, we have now known that the decay constant is equal to V alpha by 2 Rn into T, and if I find the log of it, log of alpha will be equal to log of V alpha upon 2 Rn. The multiplication will become plus log T, and we can easily compare this with the Geiger-Newton law. Okay, log of lambda is equal to log of R plus the constant which was there. So obviously the log of T is the constant here, and the other things can be compared, the range can be compared to the velocity, okay, directly to the velocity. So what do we learn from this particular Gamow's theory is that if the nuclide is short-lived, look at this expression 1, okay, look at the expression 1. If the nuclide is a short-lived one, okay, what happens if a nuclide is short-lived? Means it is very highly energetic, velocity will be high, okay. So indicates that the probability of transmission barrier penetration for an alpha particle must be high. So if the nuclei is short-lived, means it will have very high energy. So obviously its probability, very clearly you can see in the equation 1, okay, if short-lived, okay, if it has shorter long range, will have a long range. Okay, short-lived means high velocity, then obviously its transmission probability will be very high, which is expected. So, okay, so for a particle to pass through the barrier, it will have to be a short-lived one with a very high energy and a very long range. This was what was understood from the Gamow's theory of alpha particle. Okay, so hence it can be inferred that alpha particles which penetrate through the barrier at point of smaller width must have high kinetic energy, hence their range is long. Fine. Okay, so this was what we understood or concluded from the Gamow's theory of alpha decay. So that's it about the Gamow's theory, and we have these again some more references that is recommended for you to listen to, read, go through if you are interested. Again, most of this lecture is been prepared using the book S.B. Patel. All right. I hope you enjoyed this module too, and thank you.